We are ready now for Chapter 6. Chapter 6 is going to deal with physical and chemical changes. So we're going to look at some examples of physical changes or physical properties that we can look at. And then we're going to look at some of the ideas surrounding chemical changes in a chemical reaction. So the first thing we're going to talk about is, again, those physical properties. We're going to look at phase changes. And then we're going to really delve into those phase changes and talk about why each of those occur. And then we're going to take one of those phase changes, or one of those phases, we're going to look at gases in particular. So first little part, all about phase changes. Now, ever since you were a little kid, I know because my kids have all come home talking about these, you've known about the three states of matter. You've known about those for years, but we get to go back over them anyway, just to refresh the knowledge and maybe add a little bit to it. So traditionally, we talk about the three states of matter. We have solids, liquids, and gases. Now you guys are familiar with a solid. A solid is something that's going to have a fixed volume and it retains its own shape. So it doesn't matter where you put that object at, it's going to stay the same shape and it has the same volume. On the next slide, we're going to look a little bit about the reason why. Never mind, let me do it now. So that solid, if you can imagine, we have all of these atoms and molecules that are lined up and they're really close to one another. Now, they're still moving, they're still vibrating because they're never going to completely come to a standstill. But they are so tightly packed in there, there's nowhere for them to go. So that's why the solid is going to keep its shape. Now, if we could give that object a little more kinetic energy, those molecules or atoms or ions, whatever they might be, can actually move past one another. They lose what are called intermolecular attractions and they can flow. So they're still pretty tightly packed, but not as tightly packed. They aren't like stuck in a seat. They're able to move around a room. A lot of times I use a classroom as an example. The students in their desk, which are very nicely arranged in a three-dimensional order type thing, two-dimensional, that's going to be your solid. But if the kids get up and they start moving around the room and they can flow past one another, that's a liquid, but they're still pretty close to one another. So the liquid has a fixed volume, but it adapts to the shape of the container. So if I am making brownies, I'm going to take my oil and I'm going to measure out a half a cup. Well, that oil went from the shape of the bottle to the shape of my measuring cup to the shape of the bowl that I put it in. But the volume is going to stay the same. Otherwise, what would be the point of measuring out a half a cup? So the volume remains the same, but the shape can change. Now, the last one we're going to talk about is a gas. And a gas is, okay, back to our classroom example. At the end of the hour, I say, okay, guys, see you tomorrow. And everyone heads for that door and they scatter all over campus. That's a gas. There's lots and lots of empty room in between those different people, those different students, in this case, the different atoms and molecules. In fact, there's so much empty space, we actually start to ignore the volume of the gas molecules themselves, giving you a bit of a preview there. So we'll say that gases adopt the shape and volume of their container. You can compress them, you can force them to be closer to one another. They can expand, meaning that they get further apart from one another. So gases can do a whole lot, and that's why we're going to have a whole section just to learn about gases. Now, there is a fourth phase that we talk about, or a fourth state of matter that we talk about, and that's the plasma state. Now, with the plasma state, it's at such a high temperature that the electrons have actually been stripped from the nucleus, and everything exists in a hot, huddled mess. Just lots and lots of energy, things going everywhere. So plasma examples are like the interior of the sun. Lightning is an example, and even a plasma cutter uses that plasma state. But it's not one that we necessarily talk about in great detail, at least at this level of chemistry. So we want to look at those three states of matter at the molecular view. So if we could get in that magic school bus and we could go into a substance, how would those molecules actually look? Well, here we have water in all three phases, all three states of matter, a solid, a liquid, and a gas. We want to start with the gas really quick because that one's sometimes the easiest to see. So here's my gas up here at the very top. There's the gas. If you notice, there's lots and lots and lots of empty space between the atoms. And the other thing to notice is this line behind it. Well, it's not actually a line, but it looks like almost like a shadow behind it. And that's indicating that those molecules are moving very fast. Now, we call that a vector. If you ever watch Despicable Me, it's a vector. It's a mathematical quantity with both magnitude and direction. Yeah, go watch Despicable Me. It's really cute. This one's going to tell you in what direction you're going, and also the length of that shadow or that arrow behind it is going to give you an indication of how fast they're going. That's going to become important later on. So the gases move super fast, lots and lots of empty space between them. Underneath we have our liquids. So if you notice the liquids, they're closer to one another. They're not quite as energetic. They're able to flow past one another. They're not stuck in any certain spot. That would be a gas. I'm sorry, that would be a liquid. There we go. That would be a liquid. Then we have our solid, and we've got the solid over there on the left. Now with the solid, this is actually showing water, and water does some really unique things because you might think, wait a second, number one, there's little red dotted lines. Now this little bitty red dotted line, that's looking at the what we call intermolecular attractions. That are these temporary attractions that are going to occur between two molecules. And because here those molecules don't have a lot of kinetic energy, they're not moving very fast, we can start to form those intermolecular attractions. Now water, as it forms these intermolecular attractions and it becomes a solid, it actually spreads out ever so slightly. We're going to learn more about the reason why here in just a little bit. So it has almost like these little pockets in the middle. It likes to form these six-sided figures. But one thing that you will notice is everything is arranged in a very, very orderly manner. So if you compare that solid to that liquid, the liquid is very disorganized. The solid is very organized. And a lot of times you'll have the molecules will face a certain way just so that we can really maximize that relationship that they have. So as you go from one phase to another, what we want to do is we want to look at how the kinetic energy is going to change. So the kinetic energy is the energy of motion. So as you go from one phase to another, one state of matter to another, that is a physical change. There's no change in the chemical composition. It's still exactly the same compound, but it has different amounts of energy. That's all we're really looking at. So let's look at some of the different ways it can go for, or how it can gain that kinetic energy. There's different types of kinetic energy we could talk about. The first one's rotational. Well, rotational is just what it sounds like. It rotates, meaning it goes in a circle. It's kind of like your ceiling fan or an ice skater, and as they turn in a circle, that's your rotational. It goes around a center of mass. It spins. That's rotational. Vibrational is like an oscillating spring. It's where it goes back and forth, back and forth, back and forth, back and forth, just right back and forth over and over and over again. That's vibrational. Now we're really looking at translational, and translational is whenever it moves from one location to another. And so if you increase this translational energy, we really get to see how those molecules are going to move around a substance. So we're concerned most with translational kinetic energy. Now, each of those atoms or molecules or ions that you have in your substance, they each have their own kinetic energy. It's kind of like when a class takes a test. Each student had their own score on the test. But as a teacher, what I can do is I can average those test scores together to get an idea of how the class is doing. We do the same thing with our atoms and molecules. If we take an average of all of those kinetic energies, we come up with the temperature. That's all temperature is. I love that definition of temperature, the average kinetic energy. So if all of your atoms and molecules gain kinetic energy, they start moving more, we're going to see an increase in the temperature as a result of that. Now, continuing on with these phase changes of going from one state of matter to another, we're going to look at some of the special names they have for those changes. The first thing we're going to do is look at what happens when you melt something. Well, if you melt something, you're going from a solid to a liquid. You guys know that. And you know that when you go from a solid to a liquid, you have to add energy to make that happen. You have to heat up that substance. That means that melting gains energy, or we have a special term for that. Do you remember it? That's endothermic. We have to add energy to make that happen. Now in that column, there's a bunch more endothermic reactions, phase changes. Now the other thing we could look at is what happens when it releases energy. When it releases energy, do you remember the special term? Oh, that one is called exothermic. Now this means that it releases heat. Now sometimes it's hard for our minds to wrap around this, but we'll see what we can do. All right, so when something freezes, sometimes we call that fusion. So freeze or fusion, same exact thing. That means that that substance lost energy. It released energy. Now in your mind, you're like, okay, if water freezes, it's getting colder. Well, for it to get colder, it actually had to release that energy. Sometimes that's hard to, like I said, kind of wrap my mind around. So freezing is actually an exothermic reaction, exothermic process. So going from a liquid to a solid, that freezing or that fusion is exothermic. We're releasing energy for that to occur. And if you think about it, you got the molecules kind of, they're close together, but they're flowing past one another. And we're going to slow them down to where they more or less stay in the same spot, still vibrate, they still move a little bit, but they can't really go anywhere. Now, the next level that we want to look at is going from liquid to gas. Now, if you go from liquid to gas, we call that evaporation. So we take that liquid, let's use water as an example, and we heat it up some more. Oh, now if we heat it, we're adding energy. That's going to be endothermic. Evaporation is an endothermic process. We have to add heat to make that happen. And what will happen is that the little molecules, they're liquid, they're flowing past from one another. We're going to give them enough energy that they can completely separate from one another and enter into this gas state. They have a certain threshold of energy that they have to have. Now, if you have a gas and you cool it down, so exothermic because we're releasing some energy, we're cooling it down, it's going to condense, or condensation is going to occur. So examples of condensation. Now it's not going to happen on this one. This is an insulated cup. Well, it did a little bit. Now occasionally, have you ever noticed condensation on the outside? Now I'll admit I wasn't really smart as a child. I thought that was like liquid leaking through the styrofoam. Yeah, that can happen in some cases if you leave it long enough. But usually what happens is because what's inside the cup is so cold, it actually cools the air around your cup. And so any excess water vapor is going to condense, and you'll see it on the side of your cup. That's kind of cool. So that's condensation. Let's go to another phase change. Let's go from a solid directly to a gas. Now this is an unusual one. We're not going through a liquid state. We go from solid directly to a gas phase. That's called sublimation. So some examples of sublimation, let's see here. Dry ice. So dry ice, if you go and buy it at the store or wherever, it's a solid. And then when you open it up, it's solid carbon dioxide in case you were curious. When you open it up, it goes to this gas phase. You have like this fog that starts to occur and it's really cool looking. It never changes to a liquid. It goes straight to a gas. That's sublimation. Other examples of sublimation, naphthalene, which is in like the old style of mothballs, that will sublime. It goes from a solid, and then you get the vapors that come off of it to help protect whatever you put the mothballs in. One more example, an old light bulb. In an old light bulb, the filament was made out of tungsten wire. And when you send the electricity through there, it's going to heat up that wire until ideally it's going to glow. And so you're going to be able to see the light that comes off. And then there's a lot of heat that's lost off of that also. But what happens with that tungsten is if it gets enough energy, it goes from a solid and it jumps directly to a gas phase. So in that sealed light bulb, there's all of these gas particles of tungsten. And as they start to cool down, they're going to redeposit, or it's called deposition, on the side of that light bulb. And you would see that as a dark spot. So in the old style light bulbs, when you'd see that dark spot, and someone might say, oh, my light bulb burned out. Well, the light bulb burning out was actually that filament. It had so much sublimation, so much of the tungsten had left that it got so thin it eventually broke. And once it breaks, you can't complete a circuit, light bulb won't come on. Those dark spots are where the tungsten redeposited on the side. Another example of deposition, frost. So if you see frost outside when it gets a little colder, that's actually water vapor, so H2O vapor, gas state, that is going to go directly to a solid. It doesn't go through a liquid, so it's not like it condenses on your plants and then freezes. It actually forms ice crystals to start with. So kind of a cool little thing there. So those, lots more information about your phase changes than you probably ever thought about. Now, this particular phase change is looking specifically at water, and water does these absolutely crazy things. Oh, yay, I've got my little water kit here. So water looks like this. So we've got oxygen, and we have two little hydrogens, and it's in this kind of a bent shape. But what happens is that the oxygen really likes the electrons, and the hydrogen really doesn't care. So we have this unequal sharing, or we have these partial positive and negative parts. So if you get two water molecules close to one another, they are going to form a temporary attraction. Now, it's not a bond. I can still separate it. So not a bond at all, but it is a temporary attraction. Now, because of that with water, and we're going to talk about those temporary attractions over the next section, what'll happen with water, let's see if I can add a few more here. It likes to form almost a ring-like structure when it solidifies, when it freezes. It likes to form these six-sided structures. And that's why snowflakes always have six sides, because of that. At least that's the way the story goes. And if we want to melt this, well, we have to break those intermolecular attractions. Now, the other cool thing about water is that when it freezes, so when it goes from a liquid to a solid, because it does like to form that structure where there's almost like a circle in the center, a little pocket in the center, it actually expands when it freezes. Water is one of the very, 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 very few substances that do this. For most substances, they are most compact whenever they're a solid. Now, this is going to affect the density of the substance. It's going to affect, usually if something is, you have a liquid and a solid version, the solid sinks. Water doesn't do that. Water is actually going to float to the top. water is just this crazy, crazy substance. That's why we have to be careful of water when it freezes in the pipes, because it'll make your pipes burst. So if it gets close to freezing, depending on where you live at, they might tell you to leave your faucet drip just a little bit so that that water, because it's moving around a little bit, doesn't have a chance to solidify. So just be careful with that. So that is a little bit about phase changes.